A very important element of any kind of structural engineering is considering the soil mechanics, the soil properties upon which a structure is going to be built. Depending on the nature of the soil, whether it's rock or whether it's sand or clay, whether there's water permanently present or not, has a real impact on what type of foundation is going to need to be built and the construction of the building itself. Now, an obvious example of soil properties affecting a structure is the Leaning Tower of Pisa. So what happened there was the tilt was caused not because they built it crooked, but because the upper clay layer beneath one side of the tower became compressed, and so the tower started to lean. And so the compressibility of soils and the impact of the water saturation within that soil varies from material to material. And so if we think of a sponge, if we have a sponge that then absorbs water, when we squeeze that sponge, it releases that water and it retains its skeletal structure. So it might be impacted a little bit by that squeezing, but not in any meaningful sense. Soil, on the other hand, when you apply a load to it, depending on the type of soil, it is almost certainly going to be plastically and permanently deformed under that load. And so here we see a diagram that tries to demonstrate the idea that whatever soil you have, whether it's dirt or clay or sand or whatever, there's still going to be space in between the larger particles of that material that is normally filled with air, but then if there's rain or a water source or whatever, water fills that space, and then that water eventually is removed through evaporation or pumping or whatever. And so then the question is, what happens to the soil skeletal structure once that water is removed? So when analyzing soil, we have to consider a new set of vocabulary and various properties and variables. So the first of those is what we refer to as weight density, or just the density of a soil. So the general use for a variable for density is the Greek letter gamma. It doesn't really look like one there, but typically it looks something like this. And so the density of a material is going to be the weight, so remember that's a force, so weight per unit of volume. Now in the case of a soil, which is not a solid material, it has both the soil particles and then the empty space, the air space between. So we've got a quantity known as porosity. So the porosity of a soil is a measure of the volume of the pores divided by the volume of the total material. So we've got the volume that's occupied by the actual molecules of the soil itself. We've got the volume of the empty space, and then we have the total volume, which is the sum of those two. So the porosity of a soil is the measure of the volume of the pores divided by the total volume. So that, of course, is going to be a number less than 1. Now in a dry soil, we talk about the dry density, but then if it's saturated with water, we have what's called the saturated density. So for a dry soil, we have this dry density, so gamma dry is going to be the weight of the soil particles divided by the volume. So again, density is that force per unit of volume. So here for the dry density, we're talking about just the weight of the soil divided by the volume. But if we want to get what the saturated density is, well, now it's going to be the sum of those two weights. It's going to be the sum of the weight of the soil plus the sum of the weight of the water that's filling those pores. Because under normal circumstances, those pores are filled with air, but if we're saturated with water, then we're going to have a water weight there as well. So we have to add those two weights together to divide that by the volume to figure out what the saturated density is. Now, to calculate that using that porosity variable, we can do a little bit of substitution here. So for example, here I've got the dry density, if I just take the weight of the soil divided by the volume, and then if I add to that the weight of the water in the pores divided by the volume, and do a little bit of substituting, I can replace that with the porosity times the density of water, And so now I have a mechanism to find what is the density of the saturated soil. So it takes into account the dry density plus however much space there is for water to fill. So we factor in the porosity and then the density of water, so that will get us to the saturated density of a particular soil. So what we see in front of us here is a table of a variety of dry densities of sand, clay, and silt, and then their corresponding porosities. And then down on the bottom of the table we've got the density of water. So we have a dry density list. Of course, water's not dry, but you get the idea. So we want to calculate what is the saturated density of each of these materials. So if we want to find the saturated density for, let's say, the sand, so we're going to take our formula there that we had, the dry density plus the porosity times the density of water. So in the case of sand, we've got the dry density there is 94.8, and then we're going to add to that the porosity times the density of water. So in the case of sand, it's 37.5% empty pores. So if we fill those with water, now we multiply by the density of the water, 62.4, and so we get a answer of 118.2 pound force per cubic foot. Again, a force per unit of volume. And so we can do the same type of calculation for clay and then as well for silt. So the saturated density for clay, if we take the same approach, so it's going to be that 74.9 plus the porosity 0.550 times the density of water 62.4. So we're going to end up with 109.2 pound force per cubic foot. And then in the case of the saturated density of silt, so same process, dry density plus the porosity times the density of water, we'll get an answer of 106.4 pound force per cubic foot. So you can see that the once we fill those pores with water, when we have a saturated soil, the weight of the soil material is going to be significantly higher than it is when it's dry. And so that's going to affect, in theory, the property of the material when that water is present versus when it's absent. And so you have to consider this as one of the many variables when building a structure.